Hey ATM, this is going to be a video for 4-6. You may notice in your textbook that 4-6 does not have two sections to it, meaning there's not a class and a group day. It's strictly just a group day. So this is just going to be one lesson for 4-6, one video lesson for 4-6. So here once again are my lesson tips. Hopefully you've watched the first two videos and you've already read these lesson tips, but if not, take a quick peek at them and let's get started. All right, so as I mentioned, there's only one section for 4-6, so there will not be two videos, there will only be one. And the group portion for 4-6 is kind of considered a lab where, and I'm not saying we would have done this in class because we would probably have bouncy balls flying all over the classroom, but we were supposed to experiment with bouncy balls and basically throw the bouncy ball and measure the height for each bounce, which I feel like that would be close to impossible. So we probably wouldn't have done it in class anyway. But what we're going to do is use the data that the textbook came up with when they did the experiment. So as you can see from this initial table, based on the number of bounces, what the bounce height is for each bounce. So as you can see, and hopefully you kind of have known, when you throw a bouncy ball, the first bounce is always the highest, and then it starts to go down from there until eventually it stops bouncing and it just is on the ground or on the floor. So what we're going to do is we're going to take the X, which is the number of bounces, and the Y over here, which is the average bounce height for all the trials that they did. So we're going to sort of steal this data and answer the questions. All right, so I'll keep that data handy. I also want to mention is we're not going to do all the questions. We are just going to do what the textbook labels as part 2. So we're going to do 3, 4, 5, and then 6, 7, 8, and that's it. So we're just going to do 3 through 8, and then I'm also minimizing the homework problems as well. Okay, so number 3 says use either a calculator or a spreadsheet to find the exponential function of best fit for your bounce data. Write your answer in this form. So what we need to do is take the data from the textbook. Unfortunately, these numbers are not in the textbook. It was just in the teacher's manual. We need to take these numbers and enter them into our L1 and L2 under stat. We've done this a few times, so hopefully I can move quickly through the steps. But again, feel free to pause the video if I go too fast. So go ahead and press your stat button, and we want to edit, so press enter. And I've already entered the numbers in my L1 and L2 to make the video go a little bit faster. So pause the video if you need to enter your data. All right, after you have the data entered, we're going to press stat again. Okay, arrow over to calculate. And we're used to going to number 4 because that's linear regression, but we know that this is not creating a line, mostly just because we've been working with exponential functions, but also because number 3 specifically says find the exponential function. So on the calculator, you'll notice there's quadratic regression, that's for parabolas. There's cubic regression, that's x to the 3rd. There's quartic, which is x to the 5th. What we want is 0, exponential regression. So arrow down until you say CEXP regression. So go ahead and press enter until you get to calculate, and it gives us the numbers. We are going to ignore the R values, so don't worry about those. But the A and the B, we're going to plug those into the function that they give us up here, and we'll just round to 2 decimal places. So my function that I found is y equals 191.34 times, and then my B value is 0.81 to the x power. Okay. All right, so hopefully you got those from your calculator, no problem. Now it says use your function to approximate the height of the 7th bounce. How does it result compared to the value in your table? Does this surprise you? So we're going to go back to here. Remember that X is the number of bounces. So we want to say, what is Y? when x is 7. So we're going to put 7 in for x. So I'm going to do 191.34 parentheses 0.81 to the 7th power. And I get 43.77. Now I have to refer back to my table here. The y value is in terms of centimeters because that's the height of the ball after the 7th bounce. So I'm going to put centimeters, okay? Now, it does say, how does the result compare to the value in your table? Does this surprise you? So we got 43.77, and for the 7th bounce, we got 45. So we're actually very close. So I'm going to say very close to the value in the table. Not surprising at all. Okay, now it says find f of 0. This is going to be similar to the last question, but I'll be putting 0 in instead of 7. So I'm going to actually go back and just edit the 0, and I get 191.34. That happens because anything to the 0 power is 1. So this section here is 1 times your a value, which obviously then doesn't change. So that's centimeters. Now it says, what does your answer mean? Okay. If we put 0 in for x, remember that's the number of bounces. So this must mean that it's the initial height or the original drop height. Okay. And if we look back at our table, for 0, we had the initial drop height as 200. So again, we're not too far off. Okay. All right, let's move on to question 6. Let's now analyze the significance of every symbol in our equation. What does the variable x represent? So again, refer back to the table. X tells us the number of bounces. Okay. In the function f of x equals a times b to the x, that models your data, what is the value of a? What does it tell us about this experiment? Your answers to questions 5 and 6 should help, okay? So if we're trying to figure out what the value of a is, remember that our function is this, right? And we know that the a value is 191.34. So I'm going to say a equals 191.34, okay? And this is the function's estimate of the original drop height. Estimate of original drop height. Okay. Doesn't match the results in your table, and why do you think that is? I'm just going to say that it doesn't match perfectly. Okay, but it's close. Because remember, our data showed 200 as the original bounce height or the original drop height. But why do you think that they're not exactly the same? You have to keep in mind that the calculator gave us an estimate based on all of these numbers, right? So that's based on the 3 different trials that the bouncy ball experiment got us, right? So this could be due to experimental error. If you guys can imagine, if we had done this in class, I think it would be really, really difficult to measure how high up each bounce went. It's very hard to keep track of a bouncy ball when you bounce it, let alone measure the height of how high it goes. So it's probably just experimental error. All right, and then the last one, it says, in this function that models your data, what is the value of b, and what does it tell us about the experiment? Okay, from our equation that we got from number 3, this is our b value, 0.81. okay? And this tells us that on average, and again, it's average because it was between 3 different trials that were done. On average, each bounce the bounce height is about 81%, because again, 0.81, if you put that into a percent, multiply by 100, you get 81%. It's about 81% of the previous bounce height. Okay, and that's the last question for 4-6. I just wanted to do kind of a brief overview of exponential functions, especially with real data, and just kind of talk a little bit more about what the A and B values meant and all that. So hopefully this gave you a little bit better understanding of exponential functions. And if you have any questions, make sure you put your questions in the comment section on Google Classroom. Thanks for watching. I'll see you guys next time.